So in the previous video, we have somewhat kind of explained to you the amount of forces, that is amount of friction force, alright, that will be caused by the contact surface area, alright, the total contact areas. So we say that we want to have a lesser areas so that we will have a lesser force applied onto the two surfaces that will cause frictional and eventually causing more frictional forces that will wear the materials, alright, that will cause the material to be worn away, alright, and things like that. But nonetheless, let's continue back to the next one, where we'll talk about the Bowden and Tabor theory, alright, where we will go into the equations, and the purpose of it is to actually determine somewhat the coefficient of friction, or the equations to determine this coefficient, alright, which is somewhat interesting, but I don't think I can derive it quite well. So just a warning ahead also is that, yeah, my explanation will be sucks, so be warned of that. So the Bowden and then Tabor theory states that there is actually two combinations of shearing and plonking components in your friction, alright. So shearing, most probably you know what the hell is shearing. So you have this material, and then after that when you shear this thing, this dude over here will actually move like that, so you kind of shear it. Alright, so what about the plonking? Plonking is a little bit slightly different. Only if you watch those criminal show, or when there's a blood stain and then they will just wipe away the blood stain. So normally when they wipe away the blood stain, there will be some form of this type of thing, or you drag the dead bodies across the floor, or maybe this is some dead bodies, he's dead, alright, and you're just dragging him along, then his blood is all along here. So this type of dragging is actually called the plonking, alright, the plonking, alright. And as you can see, although there is certain form of plonking, there is also a combinations with shearing, which is what they're trying to say, because you're dragging across. Let's say this is the dead body, alright, maybe he's really dead, so you drag across this thing, so the floor over here may actually be how do I say okay, so this is the floor, alright, this is the floor, and maybe the floor has to be more like that. Okay, so maybe this portion over here is causing the friction, right? So when you start to drag, alright, this part over here will also try to pull this particular surface, alright. So if I were to start to drag this thing, because of the welding, alright, if you remember the previous video we talked about the welding, the micro welds. Nonetheless, if I were to start to drag, alright, as you can see, there is certain form of the part of the floor being dragged out, alright, you see there is certain part of the form being dragged out, because this is more on the form of shearing, alright, you see the thing. So I think you kind of like know what I'm trying to say already, alright. So it's trying to shear away some of the portion of the floor, although I'm being super exaggerating, okay, but at least you get the meaning of the combinations of plonking and what's that called, shearing, alright. So therefore later on you'll get to see that the total friction force is considered together with the shearing and the plonking. P for plonking, shear for shearing, S for shearing. Okay, but before going into there, let's continue to talk about this, alright. So so it says that consider a contact between a hemispherical rider, or hemispherical is just half of a circle, alright. So if you take a look, this thing over here is half of a sphere, alright. Hemisphere is just half of a sphere, alright. Spherical is just a sphere, alright. Half of it is just half of it, so this is half of it, okay. So this half of it, right, is a rider, alright. It's not Ghost Rider, it's a rider. So this rider is normally a harder material than this soft material over here, alright. This thing is a soft material. So you rub across the rider against this soft surface, and the shearing component is this one, alright. S shearing component is equals to A times S. This is the shear forces, alright. So we should say that this is tau. No, sorry, paiseh. This is shear force, alright, just only force, okay. So how does this relate to the previous things? This you may forgot. Alright, so this is coming back from the surface contact about 2 or 3 videos ago. You can search it out yourself. Alright, so we also got talk about the shearing effect. Alright, but however this is talking about shear stresses. So don't confuse yourself with the shear forces. Alright, this is the shear forces, this is the shear stress. Alright, where it is equals to K. Alright, so just now, so over here there is a way that is saying that this thing over here is equals to K. So there is a certain relationship in there. Alright, so you need to know where they are being applied. Okay, but do take note that over here at the surface contact, alright, this is for the two curved surface. If you remember, you can just search for the keywords. Or you should get you should know that your maximum shear stresses should be U stress divided by 2, which is equals to K, like a certain coefficient constant, I think. But nonetheless, coming back here, alright, you don't need to care much. You just need to know that this is the thing. But in fact, you don't need to know anything, because I don't think he say that this is not very, he will not come out this in exam, but good for you to know. So nonetheless, this is the shear forces. Alright, and there is additional forces is needed to displace a wall of materials ahead of the sphere. Alright, so imagine you have certain because you already indented, alright, so you have already caused a certain impression onto the surface. At first also like that, then you put the ball on top, yeah, so the thing become like that. Okay, so if you become like that already, if you want to slide across, alright, you need a certain force to move away this part. Alright, you need to displace a wall of materials ahead of the spear, right? So you need to remove this amount of material. So therefore you talk about the prime, alright, A prime SY. So this A prime is a projected area that you will the area that you will rub across, alright, the area that you will rub across it. So nonetheless, if you think about it, everything over here is talking about stress is equals to force over area. It's just keep on changing the terms here and there, like very flowery, like A prime lah, AT lah, S lah, SSY or whatever. But still talking about stress. This one is shear stress. F instead of force, they write shear. Alright, but it's still a shear force, type of thing. So you need to know how to interpret this thing in an easier way. So A prime is equals to D cubed over 12R, some projected area, AOBC. Alright, so I will believe that the AOBC is coming from AOBC. So it's this amount of area. I don't know how it's gonna be calculated, but just bomb only. You just need to know this lah. So in case in the future you want, you can just elaborate further. Alright, so let's continue. And in fact, coming to think about it, I think this thing is actually called P. Alright, yeah, take a look, you give me a while. Yes, it's called P. So there is a careless mistake over in the slide also. Alright, this is what I realized, a bit weird. But so this is not the shearing anymore. This is the plugging forces. Alright, because you are trying to plot the material. Oh, there's a clearer way. So the plugging meaning is that you're trying to remove the amount of material in front of you. So this is the meaning of plugging. Ta-da! Yeah. Anyway, so yeah, take note that is cancel is P. Alright, but nonetheless, so the total force includes the S and the P, which we have said. So the total friction force is this dude. Alright, but for small load, alright, the plugging is kind of negligible. So this is why we cancel this and we only look at this. So the total force is this dude over here. Amount of area, alright, multiplied by the shearing of the U strength. Alright, most probably, yeah, shear component. Okay, so in order to determine the coefficient of friction, alright, the coefficient of the friction is this, alright, this is the normal forces, alright, so there will be a certain coefficient is equals to the friction force, alright, so this is the thing. So if you bring this weight down, alright, then you'll talk about the coefficient F divided by the weight, alright. Eventually you kind of know that this is the area, this is the shear stresses, this is the area, this is the U stress. So it's a ratio between the good question. What is SY? You give me a while. So coming to think about it, right, I think this one, right, this is the yield stress of the softer material. So I repeat again, this is the yield stress of the softer material, so this is why it's SY. Okay, so therefore the area, alright, projected area times the shear stress of the onto the soft material divided by the area, projected area, alright, multiplied by the yield strength of the hardened material. Okay, so this in total, this is the yield strength of the soft material divided by yield strength of the the hard material. Alright, so hopefully this is pretty clear. So it's just a ratio. So this is all in all trying to tell you how to find the coefficient of friction. And it just need you to know is that the presence of the oxide layer kept the coefficient friction as 0.2 for most metal. Alright, so this oxide layer is what it's kind of do is, because if you remember, this is the particular surface, right? This is the material one, alright, and then this is the softer maybe I should say that they have the other color. Over here, this is another material, alright, but because when you slide, alright, there is a load W, right? So when you're sliding this over here, alright, the interface between them will cause certain micro welds, which we have said just now, right? So the micro welds, in the previous video, so the micro welds actually cause this type of oxide layer due to chemical reactions of heat and everything. So they will cause this type of oxide layer. So this oxide layer itself will generate the form of friction coefficient of 0.2. Alright, so why is most metal coefficient 0.2 is because, or around 0.2 is because of this oxide layer, due to the coefficient, due to the sliding effect lah. Okay, hopefully this is pretty clear. So I don't know whether am I right or wrong, is that the depositions of the soft metal on the hard substrate will lower the shear stress. Right, so I think the oxide layer itself, to a certain extent, over here is absorbed oil molecule. Alright, so over here, this oxide layer is some form of a lubricant to a certain extent. So that this is the harder part. Alright, this is the softer part, for example. So the softer part, alright, we're rubbing against this oxide layer. Alright, at least, how do I say? This is the soft one, this is the hard one. Along time, the soft and the hard rub against each other will create this type of a layer, where this layer is in fact softer than the hard one. Okay, I don't know. I'll leave you to think about it a bit chim because of the sentence. Alright, let me see. This sentence, alright. This is consistent with the fact that the friction coefficient of a wide range of metals do not greatly vary. Okay, so it's okay, still 0.2 for most metal, coefficient of friction. Alright, but this theory also explains why a low coefficient of friction can be obtained by depositing a thin layer of a soft metal onto a hard substrate. So if they deposit a thin layer of a soft metal on the hard substrate, alright, it's found that the shear stress relates to the soft metal, while the yield pressure is governed mainly by the harder substrate, and the ratio is low. In order to give this ratio low, alright, this thing over here, the harder substrate, must be very high. If this is very high, then you will give a very so-called low coefficient. Low coefficient means that you can easily pull the thing apart, because this thing is so hard, alright, that the top material is so soft that you can just easily slice it off. Alright, you can easily move along with it. Alright, so you have no any friction force against it. Alright, so the softer material, the softer better, so that you can slide it easier. For example, you have some tofu. Alright, you try to take your hand and move over this tofu. This tofu can straight away, the friction coefficient of the tofu against your hand is way low. Alright, because you can easily slide through it. I think you get what I mean. So yeah lor. So you can actually rig out the lubrication also. Alright, you can, when you put in the lubrication film, alright, when you start to create this type of protection layer, on the surface of the material, you can reduce the coefficient to 0.01 or smaller than that. And lubrication can be full, mix, or boundary, or determined by the extent of the load. So please take note of these key terms: full, mix, and boundary. Alright. So I search for the picture full fluid film. So this layer, I believe, is the oil. Alright. So you fully isolate both materials. Mix is that you allow some of the asperatus, these high peaks, to meet each other, while some of the stuff are lubricated, or it's not totally lubricated. Boundary one is really just a thin layer, just the boundary will do. Alright, fills the valleys, but there's still a metal to metal contact of opposing peaks. Alright, so all in all, this thing uses more oil, alright, more lubricants. Alright, so this is the better one, but not necessarily the best, but in terms of cost, everything you need to consider. But yeah, so I think you kind of get what I mean. Okay, and still got what? The more exact one, right? The mixed film lubrication mix with oil film and additive boundary film. So the boundary isn't just oil. I think it's a special type of additive, a special form. So it's at least you can reduce the amount of thickness, or I don't know, but yeah. So over here, this is the boundary, and then the orange color one is the oil film. Alright, so this is the mixed one. Alright, and cyclic loading, connect loading will cause pitting and flaking. So linked to wear and tear lah. So this is the type of flaking that is talking about pitting. Alright, pitting. And then flaking is this type. Alright, hopefully I think you know what I mean already. So you need to know that the lubrications will reduce the adhesive wear significantly. So adhesive wear is the adhesive between the interface, or there will be a certain adhesive. So when you to a certain extent, I don't know how it works, but yeah. So friction loss is that the friction force is independent of the apparent area of contact and proportional to the applied load only. Alright, so F is equals to area times stress. Alright, so proportional to the applied load. So the applied load may be amount of force. Alright, this is the frictional force, this is the load, the stress. So yeah, so the force is very dependent on the stress, but why is it not dependent on the area? Maybe because area is uncontrollable, I don't know, and I'll leave you to think about it. And then the coefficient of friction is independent of the applied load. So this is the force equals to, this is the coefficient of friction, and then this is the applied load W, coefficient of friction. So the applied load is W again. Alright, it is independent on, I don't know, yeah, I'll leave you to think about it. And then kinetic or dynamic friction. So kinetic is talking about moving, alright, half mv squared, something is moving, velocity. Alright, so dynamic friction force is independent of velocity. Like, independent meaning what? Alright, should say all along all these things, or this friction law thing, they are talking about irregular of your amount of load that you put in. Alright, no matter how you put in the load, alright, at the end of the day, or no matter how you have certain amount of area of contact, end of the day is talking about amount of coefficient of friction. If you have a coefficient of friction in between the layer, the lubrication, alright, you can actually reduce the friction quite significantly. Alright, so therefore I'm kind of thinking that's the meaning of that, of the independent here and there. Alright, so all the weight, the load, alright, or the area aren't something that will contribute to the friction forces. Alright, but the friction forces are contributed by maybe coefficient of friction, for example. Alright, and the lubrication, I don't know. Yeah. And the velocity most likely is the shaft and the bearing. Alright, this is the shaft, this is the bearing. So you turn, I don't know. Yeah, a bit shag. Yeah, I am really weird. Yeah. A key takeaway you should check it out is the amount of the oxide layer is 0.2 coefficient of matter. Okay, you should check it out lah. Alright, give it a mind in mind. And maybe you should know about the theory of this thing, the shearing and the plonking. Plonking is to plow away the material in front of it. At least I learned something. So it's quite, for me lah, educative now. Alright, so yeah. And then talk about the lubrications lah. So do you suggest that you use mixed phlegm lubrication or what? And then you need to talk about it, I think. But all in all, he didn't emphasize, the lecturer didn't emphasize much. So, but I do emphasize that it may be important in the future. So yeah, I think that's it lah. See you soon.